Hello and welcome to Astronomy Daily, your cosmic connection to everything happening beyond our atmosphere. I'm Anna, and I'm thrilled to have you join me for today's journey through the latest developments in space exploration and astronomical discoveries. We have a busy episode today with fascinating stories from across the solar system. SpaceX has revealed what went wrong with their Starship Flight 8 mishap back in March, and they're already gearing up for Flight 9 with some groundbreaking innovations, including the first reuse of a Super Heavy booster. We'll dive into all the details and what this means for the future of their ambitious program. Speaking of SpaceX, they've also been busy with their Starlink constellation, recently celebrating their 450th successful Falcon 9 landing, an incredible milestone in rocket reusability. Then we'll venture to the moon, where scientists have been puzzling over a magnetic mystery. From there, we'll travel to the Red Planet, where researchers may have finally solved the case of Mars's missing water. Finally, we'll check in with Japan's Resilience lunar lander, which just captured stunning images of the moon's south pole as it prepares for a historic landing attempt on June 5th. So whether you're a casual space enthusiast or a dedicated amateur astronomer, there's something for everyone in today's Cosmic Roundup. Let's get started then with today's news. SpaceX has finally shed light on what caused the failure of their Starship vehicle during its 8th test flight back in March. According to details released on May 23rd, the mishap had a different root cause than the previous failure, despite occurring at remarkably similar points in their flight paths. During Flight 8, which took place on March 6th, several Raptor engines on the Starship upper stage suddenly shut down about 8.5 minutes after liftoff. The vehicle began to tumble out of control before eventually breaking up over the Caribbean Sea during re-entry. The timing of this failure was eerily similar to what happened during Flight 7 in January, which also experienced engine shutdowns and communications loss at approximately the same point in its journey. However, SpaceX has confirmed that these were distinctly different failures. For Flight 8, investigators determined that one of the center Raptor engines suffered a hardware failure. While SpaceX hasn't disclosed the specific component that failed, they explained that this failure enabled inadvertent propellant mixing and ignition that ultimately destroyed the engine. The cascade effect was immediate. The other two center Raptor engines shut down, along with one of the 3 outer vacuum-optimized engines with larger nozzles. With 4 of its 6 engines offline, the vehicle lost control authority and couldn't maintain its planned trajectory. In response to these findings, SpaceX has implemented several modifications to the Raptor engines for future Starship flights. These include adding additional preload on key engine joints, installing a new nitrogen purge system, and improving the propellant drain system. The company is also developing a future version of the Raptor engine with reliability improvements specifically designed to address the issues identified in Flight 8. It's worth noting how this differs from Flight 7's failure. In that case, the vehicle experienced what SpaceX called a harmonic response, essentially vibrations that were several times stronger than expected. These vibrations created additional stress on the propulsion system, causing leaks that ignited a fire in the engine bay. SpaceX pointed out that the fixes they implemented after Flight 7 to address those harmonic response issues and flammability concerns worked as designed before the unrelated failure on Flight 8 occurred. The good news for SpaceX is that the Federal Aviation Administration has provided final approval for the next Starship test flight following their investigation of the Flight 8 mishap. This paves the way for Flight 9, which the company confirmed is scheduled for no earlier than May 27th. Looking ahead to SpaceX's 9th Starship test flight scheduled for May 27th at 7:30 p.m. Eastern, the company is preparing for a groundbreaking milestone in its ambitious development program. For the first time, SpaceX will reuse a Super Heavy booster, specifically the same one that launched during Flight 7 earlier this year. This marks a significant step toward SpaceX's vision of a fully reusable heavy-lift launch system. While some components of the booster have been replaced since its previous flight, the company reports that a large majority of the hardware will be flying for a second time, including 29 of its 33 Raptor engines. Unlike the previous 4 test flights, SpaceX is taking a different approach to booster recovery this time. The company will not attempt to catch the Super Heavy booster with the launch tower arms at Starbase in Texas. Instead, Flight 9 will test new flight profiles for the booster after stage separation. These new profiles include controlling how the booster flips to orient itself for a boost back burn and using a higher angle of attack during descent. Both modifications are designed to reduce the amount of propellant needed for recovery operations. SpaceX will also experiment with alternative engine landing profiles during this test. To maximize safety of the launch infrastructure at Starbase, the Super Heavy booster will follow a trajectory toward an offshore landing point, culminating in what SpaceX describes as a hard splashdown in the Gulf of Mexico. This controlled ocean landing allows SpaceX to gather valuable data without risking damage to ground facilities. For the Starship upper stage, the mission objectives include many of the demonstrations planned for previous flights that couldn't be completed due to the failures. These include a critical Raptor engine relight while in space, deployment of 8 mass simulators representing next-generation Starlink satellites, and tests of various reentry technologies. This flight represents an important evolutionary step in the Starship program. And in other SpaceX news today, the company kicked off what appears to be a remarkably busy weekend with yet another successful Starlink satellite deployment on May 23rd. A Falcon 9 rocket blasted off from Vandenberg Space Force Base in California at 4:36 p.m. Eastern, carrying 23 Starlink satellites bound for low Earth orbit. The mission, designated Starlink 1116, utilized a first-stage booster known as B-1075, which has become quite the veteran of SpaceX's fleet. This marked the booster's 18th launch, with 14 of those missions dedicated to delivering Starlink satellites. The Workhorse booster previously supported the SDA-0A mission, Sarah-2, and Transporter 11, before becoming primarily dedicated to Starlink deployments. Just over 8 minutes after liftoff, B-1075 executed a perfect landing on SpaceX's drone ship, aptly named Of Course I Still Love You, which was stationed in the Pacific Ocean. This touchdown represented a significant milestone for the company, the 450th successful landing of a Falcon 9 booster. This achievement underscores the remarkable reliability of SpaceX's reusable rocket technology, which has revolutionized the economics of space access. Meanwhile, the rocket's upper stage continued its journey, releasing its payload of 23 Starlink satellites approximately 1 hour into the flight. Each satellite will now maneuver into its designated position within the growing Starlink constellation over the coming days. The Starlink network has expanded dramatically, now consisting of more than 7,000 operational satellites, forming a complex lattice that provides global internet coverage. This launch marked SpaceX's 61st Falcon 9 mission of 2025 and 63rd overall launch this year, when including the 2 Starship test flights. The company's launch cadence continues to accelerate, with potentially 2 more Starlink launches scheduled before the end of the weekend, showcasing the operational tempo that SpaceX has achieved with its reusable rocket fleet. Next on today's agenda. For decades, scientists have been puzzled by a fascinating lunar mystery. Why do some moon rocks show strong magnetic signatures when the moon itself has no magnetic field today? This question has intrigued researchers since the Apollo missions of the 1960s and 70s, when astronauts returned with rock samples that exhibited unexpectedly powerful magnetization. Recent computer simulations have provided a compelling new explanation for this phenomenon. The research suggests that massive asteroid impacts billions of years ago might have temporarily amplified the moon's ancient magnetic field, essentially imprinting a magnetic signature that's still detectable in lunar rocks today. The moon once had a weak magnetic field generated by its small molten core, but according to researchers at the Massachusetts Institute of Technology, this field alone wouldn't have been strong enough to magnetize surface rocks to the degree we observe. However, a powerful asteroid impact, quite possibly the same collision that created the massive Imbrium Basin, could have dramatically changed the magnetic environment, if only for a brief period. The simulations show that such an impact would have vaporized surface material, creating a cloud of superheated, electrically charged particles called plasma. As this plasma enveloped the moon, much of it would have concentrated on the far side, the opposite side from the impact. This plasma concentration would have temporarily amplified the moon's magnetic field in that region, allowing rocks to capture this short-lived magnetic surge before the field faded away. Isaac Narrett, the graduate student who led the study, explains that this process could account for the majority of strong magnetic fields measured by orbiting spacecraft, especially those detected on the far side of the moon. The research team believes the impact would have triggered powerful seismic shockwaves that swept through the lunar body and converged on the far side. These waves likely jittered the electrons in nearby rocks at precisely the moment the magnetic field peaked, effectively locking in the field's orientation like a geological snapshot preserved for billions of years. Professor Benjamin Weiss, a co-author of the study, likens the process to throwing a deck of cards into the air while a magnetic field is present. Each card has a compass needle, and when they settle back to the ground, they align in a new orientation. That's essentially how the magnetization process worked. The most fascinating aspect of this research is that the entire sequence would have played out in less than an hour, yet left behind a magnetic signature that has persisted for billions of years. Future lunar missions will soon have the opportunity to test this theory. The most strongly magnetized rocks are located near the moon's south pole on the far side, precisely the region that several international missions, including NASA's Artemis program, plan to explore in the coming years. If these rocks show evidence of both shock and ancient magnetism, it could confirm that the moon's magnetic anomalies were indeed caused by a colossal asteroid impact billions of years ago. Next, let's head over to Mars, where yet another mystery may have been solved. Scientists have long been puzzled by Mars's dramatic transformation from a water-rich world to the barren desert planet we see today. Now, groundbreaking research from the University of Texas at Austin may have finally solved a major piece of this planetary mystery, revealing exactly where much of Mars's ancient water disappeared to. The study, published in Geophysical Research Letters, identifies a crucial connection that has eluded researchers for decades: the pathway between ancient surface lakes and a deep underground reservoir located approximately 1 mile beneath the Martian surface. Graduate researchers Mohammed Afzal Shadab and Eric Hyatt developed specialized computer models to calculate precisely how quickly water would have infiltrated early Martian soils. Their findings reveal something remarkable. Unlike Earth, where surface water can percolate underground in a matter of days, on Mars, this process would have taken between 50 and 200 years. This significantly slower rate resulted from several unique Martian conditions: a much deeper water table, lower gravity, and colder temperatures all dramatically slowed the infiltration process. What makes this discovery particularly significant is that it represents the first quantitative measurement of groundwater travel time during Mars' wetter period, roughly 3 to 4 billion years ago. The model suggests that the amount of water lost to underground storage could have equaled at least 90 meters, or about 300 feet in global depth. Considering that early Mars likely started with an ocean only a few hundred meters deep, this underground storage accounts for a substantial portion of the planet's missing water. Even more fascinating is how this process differed from Earth's water cycle. On our planet, water constantly cycles through evaporation, condensation, and precipitation, allowing surface water to persist for millennia. Mars operated entirely differently. As researcher Eric Hyatt put it, once water got into the ground on Mars, it was as good as gone. That water was never coming back out. This one-way journey explains why Mars's surface water disappeared relatively quickly in geological terms. The water either became chemically trapped in mineral structures or froze permanently in the subsurface as Mars lost its protective atmosphere and temperatures plummeted. Whatever surface water remained likely evaporated into space through the increasingly thin Martian atmosphere. The findings align perfectly with orbital observations showing widespread hydrated minerals throughout Mars' crust and radar evidence of buried ice deposits at mid-latitudes. This research helps close a significant gap in our understanding by quantifying precisely how much water moved underground and became permanently trapped. The researchers approached this Martian mystery by creating a sophisticated soil model that represented early Mars conditions as accurately as possible. They conceptualized the ancient Martian landscape as consisting of a porous soil layer sitting atop basaltic bedrock, incorporating all available data on temperature, gravity, and soil permeability gathered from Martian meteorites and rover missions. What makes their approach particularly powerful is the use of probability algorithms that account for numerous variables, including fluctuations in precipitation patterns, variations in soil porosity, and temperature changes across the surface. This comprehensive modeling revealed that water's journey from surface to deep aquifer would have taken between 50 to 200 years, dramatically slower than similar processes on Earth. Several key factors explain this stark difference in infiltration rates. Mars' lower gravity means that pore water pressure builds up much more slowly with depth compared to Earth. Additionally, the colder surface temperatures on Mars would have significantly reduced evaporation rates. Together, these conditions slowed water's descent by approximately 2 orders of magnitude compared to what we observe on our home planet. The implications of this research extend beyond simply understanding Mars's hydrological past. The model provides compelling evidence that Mars operated fundamentally differently from Earth in terms of water cycling. Without robust recycling mechanisms to return deep groundwater to the surface, Mars essentially had a one-way hydrological system that gradually depleted its surface reserves. Once underground, Mars's water faced 3 possible fates: becoming chemically bound to minerals forming hydrated compounds, freezing into subsurface ice deposits, or in some cases, breaking down through radiation and escaping into space. This research helps scientists quantify the relative contribution of each process to Mars' overall water loss. Shadab, now continuing this work as a postdoctoral researcher at Princeton University, plans to integrate this infiltration model with global climate simulations that incorporate rainfall patterns, surface runoff dynamics, and volcanic activity. Such comprehensive modeling could test various historical scenarios, from the existence of a long-lived northern ocean to short-term flooding events triggered by impacts or volcanic eruptions. This research also has practical implications for future Mars exploration. The identification of these ancient aquifers could guide drilling operations on future missions, potentially reaching depths of up to 1 kilometer to sample what remains of Mars's primordial waters. Such samples could undergo isotopic analysis to determine precisely how much water remains locked underground versus how much chemically altered the planet's crust. As Eric Hyatt eloquently summarized, the red planet's hydrologic engine lacked the robust recycling pump that powers Earth's blue marble. This fundamental difference in planetary water systems may ultimately explain why Earth remained hospitable while Mars transformed into the desert world we see today. Finally today, a little update. Japan's Resilience lunar lander is nearing a historic moment as it prepares for a touchdown attempt on June 5th. Just this week, Tokyo-based company iSpace shared a stunning photograph taken by their spacecraft showing the moon's south polar region. The image beautifully captures the rugged terrain of the lunar surface with its many geological features and craters. What makes this particular photograph fascinating is the optical illusion it presents to viewers. While the image is filled with concave craters, they can appear convex depending on how you look at them. A common visual phenomenon in lunar photography where depressions can look like bumps to the human eye. Resilience began its journey on January 15th when it launched aboard a SpaceX Falcon 9 rocket. The same rocket carried another private lunar lander, Firefly Aerospace's Blue Ghost. While Blue Ghost completed its mission on March 2nd, becoming only the second commercial vehicle to successfully soft land on the moon, Resilience took a more energy-efficient route, finally reaching lunar orbit on May 6th after a longer, looping trajectory. The landing target for Resilience is Mare Frigoris, known as the Sea of Cold, a volcanic plain in the moon's northern hemisphere. A successful touchdown would represent a tremendous achievement not only for iSpace, but for Japan as a whole. The nation has only one successful moon landing to its credit, the SLIM spacecraft that touched down in January of this year under the direction of JAXA, Japan's space agency. This attempt holds particular significance for iSpace following their heartbreaking near miss in 2023. Their first lunar lander successfully reached orbit in March of that year, but failed during its landing attempt 1 month later when the spacecraft became confused by the rim of a crater. The company has clearly learned from this experience and made adjustments to ensure Resilience has a better chance at success. The mission's importance extends beyond national pride and corporate achievement. Resilience carries 5 scientific and technological payloads that could significantly advance our understanding of the lunar environment. The stakes are high, but after years of development and a previous setback, iSpace appears positioned to potentially make history in just 2 short weeks. Resilience isn't just aiming for a touchdown, it's carrying a suite of scientific tools designed to expand our understanding of the lunar environment. The lander hosts 5 distinct science and technology payloads, each with specific objectives to fulfill during its mission on the moon's surface. Perhaps the most exciting component is Tenacious, a miniature rover built by iSpace's European subsidiary. This compact-wheeled robot is designed with a critical mission, collecting lunar regolith, or moon dirt, under a contract that iSpace signed with NASA back in 2020. The agreement is part of NASA's Commercial Lunar Payload Services program, which aims to leverage private industry capabilities for lunar exploration. Once deployed from the main lander, Tenacious will roll across the Mare Frigoris terrain, using its specialized equipment to gather valuable samples. These collections could provide insights into the composition of the moon's northern regions and potentially contribute to resource utilization studies for future missions. What makes Tenacious particularly distinctive is an unexpected artistic element. The little rover carries a piece called Moonhouse on its front bumper, created by Swedish artist Mikael Genberg. This inclusion represents the blending of scientific exploration with human creativity, a reminder that space exploration serves both practical and cultural purposes. The other payloads aboard Resilience are equally important, focusing on various aspects of lunar science and technology demonstration. Together, they form a comprehensive package designed to maximize the scientific return from this mission, regardless of its relatively small size compared to government-led initiatives. And that brings us to the end of today's episode. From the engineering challenges of SpaceX's Starship program to the ancient mysteries of lunar magnetism and Martian hydrology, we've covered some truly fascinating developments in our cosmic neighborhood. And of course, Japan's Resilience lunar lander is poised to make history with its upcoming landing attempt. The growing diversity of nations and private companies reaching for the moon promises to accelerate our exploration of Earth's nearest neighbor. Stay tuned to Astronomy Daily for updates on all these missions and more fascinating discoveries from across the cosmos. Next week, we'll be covering the results of Starship Flight 9 and the Resilience landing attempt. In the meantime, you can keep up to date with all the latest in space and astronomy news simply by visiting our website at astronomydaily.io and checking out our continuously updating newsfeed. Until then, keep looking up. I'm Anna, signing off for today.